Well, it's my pleasure to be here. I am a true Aggie. I made my wife a true Aggie, not far from here. So those that are Aggie people know what that means, and so we're happy to see the football team doing well. They're the best 1 in 5 team in the country, I think, right now. So they've lost some close ones, which is unfortunate. This presentation, and I must say, I'm very thrilled to follow the speakers that have spoken. They've talked about subjects that are dear to me in terms of the content and the passion that's behind it. Dr. Miller and his risk assessment, it's something that I'm passionate about. I'll talk a little bit about risk. I think he said everything I would like to say. If I had his slides and my slides in that much time, it would be a balanced presentation for myself. So I'm glad he presented his information. And the work that I'm going to show is more of a higher level visionary work. The Idaho National Lab has worked in the biomass logistics area of DOE's biomass work since about 2000. And we've grown programs that house a lot of the analysis as talked about earlier, as well as a lot of the field research and laboratory research that supports the data sets that go into the modeling. And maybe a follow-up to the question that was asked previously, and I don't see the gentleman. If he didn't sit in the same spot, I wouldn't know if he was here still. But there are data sets that are being provided through what's called the Knowledge Discovery Framework, and that housed infrastructure is at actually Oak Ridge National Laboratory, and much of the data that's being produced, both field study-wise and otherwise, is being put out onto this Knowledge Discovery Framework. So KDF, or those 3 words, if you Google it, you'll find it. But that's in maybe partly response. A lot of the data that we're collecting is being put out there in database form. And so that's a start for us to try to disseminate this information more effectively. So I want to start with this graphic. We've done some international work with some universities in Europe, and this is an older graphic, as you can see, 2009. But I wanted to start by talking about what I would call a pseudo commodity, and I call it that because it's heavily subsidized. The wood pellet industry is heavily subsidized by the European governments, and they're bringing pellets in to provide heat and power for their policies that they've put into place. And as you can see there, a significant amount of wood pellets are being produced in both Canada as the #1 provider, and then U.S. slowly behind, and maybe not slowly, quickly catching up to Canada in the production of wood pellets, and all for the markets in Europe. Well, they have a policy and they have subsidies that support that. So the wood product industry, and particularly in the wood pellets, shows the ability to move biomass long distances, store it, and have it for energy use. And in terms of the feasibility, the technical feasibility of the work, there's an example that's existed for some time and will continue to exist as long as those policies and favorable markets are in place. So what does that mean for us in the U.S.? Because it's a significant resource leaving our shores and going overseas to support their energy needs. Well, I think the obvious reason for that is that, as talked about by previous speakers, we don't have policy in place necessarily or subsidies in place to support that market. And without the support of those subsidies, that pellet industry just doesn't pencil out in the U.S. And even though they've overcome some of the barriers, they haven't overcome that final cost barrier. But as we talk about biomass in general, there are certain things that we have to understand that make biomass limited in terms of market. And I think many of the speakers already have, or all of the speakers talked about many of these topics. Handling attributes and conversion attributes. So we deal with both. We deal with the first directly in terms of logistics and how do we tackle biomass, reformat it, engineer it, if you will, into a product that can be used in power or fuels production or chemical production. But we also look at the conversion attributes and the numbers that are listed there, because we need to understand or the conversion side of the house needs to understand that what we do to the biomass can affect their process, either favorably or not favorably. And so we have strong ties with our other national labs, sister labs that do conversion, and other agencies that do conversion work to now start to put standards or put markers out there that we're trying to hit, targets to make sure that the conversion process fits within what we're capable of creating for them. And it's one of these where eventually we'll join in the middle and we'll have a solution to that problem. But there's many things that's listed there that prevent us from doing that. Now, the two pie charts, and I throw this up here because here's a biomass industry, corn ethanol, that has significantly grown over the last 15 years. We're approaching the 15 billion gallon mandate within the RFS. And what does it look like when you talk about logistics? And the interesting thing is you look at, and when I talk about feedstock here, I'm talking about the price. The price to the grower to secure the feedstock is nearly half the cost of producing the ethanol. Okay? And that fluctuates depending obviously on the price of corn and what the infrastructure looks like at the time, but roughly that's the price point. About 8.5% goes towards logistics or moving corn. And why is it so low? Well, it's dense, it's flowable, it's storable for long term, and so the ease of getting it out of the field and into the refineries is relatively there. Everything's in place. And then you put 43% of that cost back to the refiners to turn it into the finished fuel. You take the cellulosic ethanol world, where any biomass that's cellulosic might fit into this pie chart, and we have a problem. We have a reverse, if you will, of a lot of those figures. So we're now, because, and we back into that 5.5%, we have about 58% tied up in the conversion process. So we know that there's barriers in taking lignocellulosic material and converting it because of its inability to give up its sugars freely as opposed to the starches. We have about 36.5% tied up in the logistics, leaving us only about 5.5% to pay the growers for the material. Well, that sort of works in the sense that it's a non-food product. There's not a lot of competing markets. There are some, but it's an underutilized product. So can you get away with something less than 48.5%? Maybe. I think it could possibly work, but right now at 5.5%, there's a problem there, and that comes back to engaging the growers in moving that material. And so the issues that we are facing is how do we squeeze more out of that 36.5%, and how does the conversion squeeze more out of their 58% to give more back to the growers? And this piece here is our logistics challenge that we're trying to find solutions to, and it all encompasses these barriers at very high levels. There's more nested under those, of course. So what do we look at today? And again, my apologies, Jared and I, the program since 2000 had a much stronger background in the ag residue. It started because we were buttoned up against the corn ethanol, and we were trying to make more value add out of the corn ethanol businesses. So this integrated biorefinery was the starting place. And as we move forward, and the forest products industry is more mature in the sense of utilizing its product for high value, utilizing its feedstocks for higher value products than is, say, the wheat straw or the corn stover or other things. And so there were higher barriers, and we come from that background. But as we move in to the woody arena more, these same types of philosophies still hold true, and we're developing the patterns, as Jared pointed out, both in modeling and in research data to support where we're headed with this. So in this graphic, and Jared showed this and talked a little bit about what we're doing, but in a conventional system where we use this as a baseline because we have a forage industry that moves residues around for livestock, and we have a wood products industry and to some degree the pulping industry and other things that move forest products. Most of those are higher dollar merchandisable saw logs or timber or pulp. But in terms of how do you access the material and bring it to a location, the baselines exist. We knew that they existed, and we have sort of what it looks like in a snapshot. The problem with that system is, as you know, energy is the low guy on the totem pole. It's the last one, I guess, to get fed because it's the low cost. You can't get much for your energy product. And so you have to make these systems more efficient. And so it's taking what we knew to be true today and advancing it to where it needs to be tomorrow in terms of logistics so you can get the price point that you need. In this system, most of the processing occurs right at the plant. So you take your raw material and you move it all the way through each of these operations until you reach the plant. Then you do your final, what do I have to have it look like, and run it through your tub grinders or run it through whatever and dump it into the throat of your reactors or your boilers or whatnot. What we're changing now as we move forward in terms of thinking about the logistics is we're removing pre-processing for the most part from the biorefinery gate and shifting it forward so that more of that operation occurs around the farm and field gates. And in doing so, you start to tackle the issues of bulk density, energy density, some of those major transportation barriers, and also stability, such as moisture management, and even some of your quality. You can start to attack that there. We heard a great presentation on biochar, and I was talking to Mr. Mueller. There he is. He's sitting right there. He made me late, by the way. I was chatting with him.
Figure.
And so we talked about biochar, some of the products that come in, and imagine the logistics. If you haul everything to some biorefinery and you make a value-add product that really belongs back on the soil, back with the growers, you have to transport all that back to the growers, and so you're causing another logistical issue. And so the philosophy is that right here, two things: very low bulk density, very broad diversity of feedstocks. Who better to deal with diversity of feedstocks than the landowners? They rotate crops, they rotate species, they understand their land, so they handle diversity on a daily, yearly basis. So we leave the diversity up front, and we start to funnel the process right through here, where we start to stabilize, densify, add value, take products off that might have value to go back, shorter distance. This transport, Jared's slide showed it, but this, maybe 10 to 20 miles is all. It's local, it's industrial, however. It could be at an industrial scale. Wow, that went fast. I'll move right along. It could be at an industrial scale where you can operate 24/7, but you're going to add value back to the rural communities. And now you move a product from here that is capable of transporting long distances and have higher value. And that's the true nature of a commodity. And now when you talk about local prices, a commodity takes care of the peaks and valleys, because eventually if your product you just can't meet a certain price point, but another area, due to their agronomics or their ability to produce the material, produces a lower cost point, somewhere the commodity system is going to average that out into an acceptable price. And you can move your biomass where you need to be. So we're talking the risk mitigation part of the supply system. And this graphic, and I'll leave it to you as you look at this slide deck later, it's complicated, but it shows that there's multiple pathways from the solid and liquid depots that can produce a solid product or a liquid product, meeting into a terminal distribution where it can go rail long distances. You may have intermediate spots that handle both and can funnel work back and forth. But the idea is that you're taking advantage of what we already know is a mature industry when you look at how grain or any other energy products today are moved. This starts to lay over the top of that. So this graphic again shows this funneling where you have a lot of variation and now you have specification. And you want to deliver a product that meets a certain specification at conversion. And the two areas in which I particularly think are important is solving barriers associated with cost-effective long-term storage, so you can store more than a year. This comes into strategic storage. We have strategic oil reserves. If this is truly an energy security issue, then eventually we're going to have strategic biomass storage reserves so that we can get to them when we need to. You can only do that if you can store long-term. And then, of course, solving barriers associated with transportation. So this 50-mile radius barrier that we face, we got to punch through that ceiling and be able to move this much further for the same cost. And that's all associated with getting the product into these specifications and solving that earlier on in the supply system. So we look at this in 5 specific areas. One is the raw biomass development. So there's plant biotechnology. Many of the USDA ARS stations are looking at this. I visited a site down in Georgia that's doing a lot with the high-yielding energy crops. Very impressive work that they're doing in engineering the plant from the biotechnology side of things. And then we pick it up on the harvest and collection and storage side, which is still a raw biomass development work. What do you do when you first contact the material and start to bring it in the front gate? Once it leaves here, this is where we can start to industrialize the process, but still leave it close to the field, where we can start to pre-convert the material through thermal treatments or other chemical treatments, where we might formulate the material, and this in terms of blending feedstocks together. They have the ability to catalyze each other, and densification. I shouldn't go too deep because I have a slide on each of those. So if we start with pre-conversion and we look at mechanical, thermal, and chemical, there's various things that can be done to affect the biomass and to add value, to change its composition, to change its flowability, to change its grindability. All of these can impact, if it's in the correct order, impact how and what you might do to reformat that biomass. So everything from size reduction and separation in your mechanical work to deep drying and torrefaction. It was talked about earlier. Torrefaction is just a continuum along that line where biochar and other things fit. You can do other treatments. This is an ammonia treatment, AFEX, ozone, other chemical treatments that also change the structure and add value. But, of course, all of this depends on cost, energy balance, value add potential, and environmental impacts. Yeah, there's always something you have to balance. But if you can balance these and get value out of them so that you can reduce your costs overall, that's the objective of doing these within the supply system. Formulation, as I mentioned again, has the potential of taking your raw ingredients. And now instead of, if you're not fixed to a 50-mile radius, you might be able to bring in multiple biomass streams. It could be ag, it could be forest, it could be other dedicated crops coming into the same facility and blending those feedstocks. We had a workshop a little over a month ago that Scott was able to attend where we were doing a blended feedstock prep. And what we found with some of our sister labs is the activation energy necessary to cause reactions to occur were, depending on the blend of feedstocks that you put in there, were actually causing a catalytic reaction, so that energy was starting off early on with one particular component, and it was starting that chain reaction with other components. So if you looked at them separately in their reaction rates, they would lag behind, but you combined them and you put them into the conversion process, and they were starting to actually energize each other and make that process faster. And so the idea here is blending either right at the source or when you're feeding it in, and the whole idea that your fractions can catalyze each other. That's a new concept that we're developing to look at how biomass can help each other, and you can gain from incorporating more resources than one. And finally, densification, and I think that needs no explanation. If you can't have a high enough bulk density and energy density, you're not going to move it very far economically. And so the idea now is to take it from a strictly logistic standpoint and go through mechanical densification processes. But the other idea is there's a lot of pressure and heat that comes into the densification process. So we're looking at what types of heat and pressure might we use after we formulated it to catalyze that process while we're densifying it and actually cause a reaction to occur that will make the biomass better. My boss, my department manager, likes to look at it like this. You have your deconstruction is kind of like gathering your raw materials. Say you're making a stew, and you know that carrots and peas and potatoes all cook at different rates, and so you've got to decide when you're going to put them in the cooker and for how long. And then you blend your recipe. What do you want out? You want a nice chili? Do you want a nice beef and stew, carrot stew, or do you want clam chowder. Well, you put your formulation, your recipe together, and then you cook it, and that's a densification process. You put it all together, and you put it in your final product, and you serve it up. Each of them have a different end result and a different need, but if you understand your ingredients and what causes each of them to do what they need to do, then you can basically come up with the end product that you want, and that's what your biorefineries are going to start to request. I want a certain product or a certain feedstock that makes my process most efficient, or at least that I can dial in and make my process efficient. So the Idaho National Laboratory, through the work of the Department of Energy, has developed a process demonstration unit, and this is one of many process demonstration units that exist within the Department of Energy. We use this to gather detailed information that we can share and validate models and move our process forward. So this is where we do the formulation, densification, testing, and try to push that envelope that we have out there that we'd like to accomplish. The components of that are listed here. Again, I'll let you peruse this, but it's modular, it's reconfigurable, so as we get industry that wants to put equipment in, we can swap out different equipment at different times to try to keep up on that technology curve and demonstrate what the capabilities are. And Jared showed this, and the point here again comes back to the risk. As we do this work, our biggest focus is how do we move biomass further for lower costs? How do we move for $72 what today costs us $112? And what's the formulation so that when it gets there, it's really worth that $72 because the conversion process can lower their costs. They have a better feedstock. And if we can do that, then we're going to meet a lot of these enabling things to the industry, such as minimizing logistical barriers, smoothing the costs across the country, reducing the supply and financial risks, establishing standardized specifications that biorefineries can count on, establishing local processing for rural development and economics. And then the last two really are market developers for local markets for multiple biomass use. And then with our international work, we're even looking at, if this is a true commodity, and we're doing this today to some degree, the U.S. trade, but we need to get this so that it's competitive and we're not mining our own resource, but we have a strategic plan as to how we're going to trade commodity biomass in its raw form. And so that's kind of a snapshot of the INL, and I was interested to know, we pelletized 15 tons of switchgrass for Jonah, and I hadn't heard from him since I knew the company had broken up, so I'm glad to hear he's still in business. We might have to contact each other again. So it's a small community. I hear names that I'm familiar with and appreciate everybody's work, and that's my presentation.
Thank you.
Thank you.
So any specific questions? Bob?